So today we are going to talk about data analysis and astrophysics. You are all fine with the previous lectures, right? There is no problem because we did not think about so much. There's any problem? Okay. So no, anyway, I think you got some flavor of what it is, and then think more if it is necessary. Now, today's thing is, so I said that this integration business, that when a sinusoidal signal is coming, you actually have to integrate the signal for some cycles in order to get enough what is called the signal to noise ratio. Okay, I'll explain what is the meaning of signal to noise ratio. Essentially, the signal should become significant. Okay. Now, how do we do that and so on? So that we will discuss. The thing is that if suppose you had a single monochromatic frequency, okay, like you have this FM radio, okay, all the channels are coming at the same time. Still, you are able to listen to only one specific channel, right? That is because you could simply go to one particular frequency and select only that frequency and listen to it. If that was the case, it is basically like Fourier transform. That suppose you have data and there are a lot of signals there, and then if you do a Fourier transform, if there are some specific sinusoidal signal embedded in the noise, there will be peaks there. That is like, now if you take a certain length of the Fourier that signal, what it is trying to do is to integrate over the whole time period for that specific frequency. So it will be like this. Okay, I will show you after some time what exactly is happening. So the primary thing was that the gravitational waves interact weakly with matter. So the detector output is going to be noisy. If we could build very sensitive detectors, much more sensitive detectors, then this should not be a problem because you would be able to see this thing. But then that will cost probably 10 or 100 times more money, which would mean that you may have to wait for 1,000 years or so. So which would be too long. Because what happens is that the money is kind of fixed. Now you have to do whatever you can do with that. That is like you have to put every effort to detect the signal with minimal cost. That means your data is going to be noisy and you have to have smart algorithms to find out signals in the data. But then how will you do that? Because if the data is noisy and signal is embedded within the noise, then how will you actually find the signal? Because you cannot see it. But you can. If you knew how the signal looks like, then you can. Or you can do another thing. That suppose you know that there is noise in the detectors, the signal is weak, but then there are two detectors which are far away, and you know that the detector noise part is not correlated, but the signal part is correlated. So by studying these correlations, you can slowly build up that thing of signal to noise ratio. So I will not get into all this. I will show you this demo that will make things clear. So suppose this is detector noise, okay, and then it's this tiny signal here and there. It's like a chirp signal. It's like amplitude and also frequency is increasing with time. Okay. Now obviously you are given this blue data, then you cannot find the signal because it's just inside. But suppose somebody tells you that, well, we know that the signal looks like this. Now can you find the pattern? This is very different. That somebody has already told you that this is the signal, what you are looking for. Okay? Then what you can do is that now coming to back to this sinusoidal business. So suppose you have a small sinusoidal signal inside in the data, it's going plus and minus. If you just average out or integrate the data, you will get zero from the signal because sinusoidal will average out. But now suppose that you took the square of this and added, then also you will not have much gain, but you will get a positive number. But both noise and the signal both will add positive. Okay, so you will not have much gain there. But suppose somebody told you the frequency of the sinusoid. Okay, then what can happen is that you take that sinusoidal signal and multiply with the signal that you have. Okay, that the signal, the noise you have, there is a signal inside, and you took another sinusoidal function, multiplied to this. Okay, and then integrated. What is going to happen is that if suppose you could exactly match the sinusoidal signal, then when the signal is positive, both are positive, and if the signal is negative, both are negative. Like you have matched the phase also, phase are positive. Then all the time you are adding a positive definite quantity. You understood what I'm saying? So suppose you had a signal of this kind with huge amount of noise in the background. If you could match this signal with a model which is called a template, then and you multiply this template with the whole signal, like at each point, even though the noise is there, what is going to happen is that the noise part is going to add positively and negatively. So it is going to average out. But the signal part is always going to add, see, when it is plus, then also it will be positive, and when it is negative, then also it is going to add the so then you will get in the end a positive definite number. So this is going to add up. And all other noise part will average out, right? This is exactly what Fourier transform does. Fourier transform means that you have some arbitrary function, you multiply that function with a sinusoid. You know how Fourier transform is. It is like any function you can write, let's say, a Fourier transform. Okay, let us use some other notation. Let's say you can write it as, let's say, if so some other function. Let's say x is some function, then it will be over 2 pi I f t dt. So this kind of thing. See, what you did to get a Fourier transform of this quantity is to multiply with a sinusoidal and integrate over time. This is exactly what it is. So if you match it, then you will get a strong signal. So this is exactly what we can do even when the frequency is not constant. Suppose in this sinusoidal case frequency was constant, but suppose it was not constant. It was like something like this, and you knew the pattern. It's just in some sense oscillatory. If you knew the shape, you could still take this whole shape and multiply with this and integrate. All you need to fix is the position, the phase. That is, the starting point should match. If you move the signal here, then it will not match. If the starting point matches, then at every point again you will start getting a positive definite quantity. It will be. Okay? So that is exactly what is done by gravitational wave analysis. This is called matched filter. Okay. So this is a filter. It's a matched filter. So you're just matching the signal. So now you will see how it works. So what is happening here is that there is no any meaning, nothing is moving. This signal templates is placed at each point and this integration is done and the value is plotted here. Okay, so you place this kind of template. So suppose this is the template. Place it here. You don't know the amplitude. Okay. That is fine. Amplitude does not matter. You put it here, then integrate over this whole time series. Okay, the value you put here. Then move the signal slightly, again do the same thing, put the value. Now when the signal, the template, exactly fits the signal, that is the starting point matches, you will get a large peak because it's positive peak, right? That's how you look at this. So it is right now almost zero because it's basically on the average zero. But as soon as it matches, there will be this peak. Okay. So this is essentially the basic the idea of mesh filtering. But it is far mesh filtering in practice is far more complicated because the signal which I said that you know the shape, actually you know the shape given the masses of the binary, the spins, the orientation, all those things. So what it means is that for each of these values, each of these parameter, uh, uh, what should I say? For each of the sample corresponding to different sets values of parameter, you have to do this exercise. So for the gravitational detection which happened first time, there were 250,000 such combinations which were used. Okay, and that is actually too less because computation, because it gets computationally limited. Because you can imagine that a very large, so for the whole data set, you have to keep doing this correlation. Okay, so you take the full data set, take one template, do this correlation for the whole data set, then take the next one and do it. It gets computationally very limited. So limited that you have to make very simplifying assumptions. In practice, the parameter space is large. Okay, let me first, I'll go there, but before that, let me show you how it is, what I mean. So suppose your parameters were only masses. Okay, now what is done here, actually this mass is not a convenient parameter. So you convert these masses, two masses, into different times. So then everything comes in the units of times. Okay, so there is something called tau naught and tau 3. Forget about whatever they are, but one depends on something called a combined quantical charge mass, more strongly and so on. But anyway, whatever it is, if you consider only two masses, then you know that there are two parameters. So this parameter space, then you tile it. Okay, because you know when you have to find those template signals for different parameters, you cannot get infinitely dense parameter spacing, right? I mean, you cannot, for every point you cannot do it. So you have to place them at with some spacing. This choice of parameters tau of tau 3 makes it kind of linear, so that you can then claim if it is linear in the sense that that more or less if you place them equally, it works. If you see mass, then at the lower mass, you have to keep the spacing much smaller than at higher mass. Higher masses, the templates are similar. Anyway, these are just technical details. The point here is that you take these two parameter space and then kind of tile it and then place templates there. So, and this template density, that how closely you have to pick these parameters, depends on your computation power, how many signals will be lost, etc. Right now, if they are usually placed at something called the 0.97 minimal match. What it means is that suppose you have a signal, okay, one template you have picked for a certain parameter value, you have a signal. Now, what are you going to place the next one? The idea is that if you can write this integral, which I think was the formula was given, it is something sort of like a scalar product. Okay, it is done in the frequency domain. It's like a scalar product. I mean, you don't have to get into too much details about it, but just that this is this x of it with the Fourier transform of the data. H is the Fourier transform of the signal, the template, and this S is the noise power spectral density. That is more that wherever there is more noise, you give less weights. But ultimately, this follows the properties of a scalar product. And scalar products, you all know, it is like a vector scalar product. So these templates act, the data and template act like vectors. Now, when do you get the maximum scalar product? When they are parallel, right? And if you normalize it properly, then this will give you one. Okay. Now, where are you going to place the next template? So, next template means that you are basically trying to see, suppose there is a mismatch. That is, the signal does not exactly match your parameter, but you want to place the template such that you don't want to miss it. Because if the signal is quite far away from the template, then the scalar product value will go down. So the scalar product is taken as 0.97 because of this reason that this corresponds to 3% loss. Okay, so there is a 3% chance that the scalar product goes down by 3%, which would mean that when you consider the whole volume, because the volume goes as distance q, this 3% loss corresponds to 10% loss in volume. In other words, that if you place this signal such that the scalar product falls by 3%, the number of signals you will lose is about 10%. So which is acceptable. Now suppose you want to go, you want to do some more exotic search with more parameters, but you don't have computation power. You may say that, okay, fine, I am fine with losing 30% of the signal, but on the other hand, I want to do this search because I may find something more interesting. There will be 70% chance of finding something more interesting, which you would otherwise miss. So these are like all kind of cooking. Like, you see whatever resources you have and you want, how much time you want to put, how much you want to impress people and things like that. And that's how you decide that what you want to do. Now, the thing is that the problem is that computation is limited and you don't want to miss the signals, because then missing signal means that your detector is not being utilized properly. So what is done right now is that there are many assumptions which are made. So a black hole, of course, has mass, but then there are spins. Okay, and then spins actually change the signal, the waveform. Now, a spin is a vector. It has 3 components. Similarly, the other black hole will have 3 more components. So in that way, there will be 6 components. But what is done is that actually there is some effective spin which is defined, which is basically the spin component along the angular momentum of the total angular momentum of the system, and that way basically the orbital angular momentum, and that way then you choose mainly one component, and effectively there is an effective spin component which is defined. So this way you are basically searching in a 3-dimensional parameter space, even though the parameter space was much more. It was 3 to 2, that is 6 plus 2, 8-dimensional. In fact, the parameter space is much more. It's 15-dimensional, because you have the direction on the sky, the distance, the orientation of the binary. The distance is actually not that important, but anyway, the orientation of the binary. Then there is the initial phase, because you don't know the binary is going like this, but when you are matching the template, it is equivalent of saying the binary was here at that time, or here at that time, or here at that time, and so on. So all those things, there are many mathematical techniques which have been developed to kind of not get into all these parameters individually. Some parameters could be easily tackled, like for example, this initial phase could be sort of tackled by doing one search for 0 phase and one for pi/2 phase, then combining them. Then this could be written in terms of the Fourier transform. So all complex parameters, all those things, many things have been done. But finally, at the end of the day, you need to search explicitly for the masses and spins. There is no other way. And spins you cannot search. So this is right now, this is the situation. So the thing is that in the future, people are exploring how they can speed up this process so that they can look for more exotic objects, which would be much more interesting. Like, the spins can tell us. So there are different formation channels for these binaries. Okay. The binaries could form. There are 2 predominant things people consider. One is that the binaries are forming in some empty regions of the galaxy, like 2 stars kind of came close, then they kept inspiring, and in the end they form a merged. Okay. In this process, what happens is that during this whole evolution, their spins, etc., all get aligned. Okay, it's like kind of like the tidal locking of this thing. So they all become the orbit gets circularized and they become like a very normal vanilla system. But then there is the other possibility is that these binaries are actually forming in very dense environment in the galaxy, which are called globular clusters. Okay, there are this very strong interaction of collection of stars. They go around each other, and then slowly they start coming closer and closer. Basically, all the lighter stars, etc., they get kind of kicked out. This way, this system. So basically, what happens is that suppose one star gets too much kinetic energy, then it will be kicked out of the system. But it goes out with a lot of kinetic energy, which means that the system became a bit less energetic, became a bit closer. So this way they come very close, and then at that point, meaning when they are very dense objects, and also this kicking out happens more for the lower masses because their kinetic energy, it is like equipartition of energy. If you have almost the same energy, the lighter ones will have much more velocity, so they get out of the system. So the heavier ones kind of start coming closer and closer, and this is called mass segregation. And then in the end, this whole cluster is full of heavy black holes, and then they keep getting to three-body interactions and so on. In that case, there is no reason for these spins to be aligned. So if we could search for the specific spins, etc., that would give us a much stronger proof whether the black holes were formed in empty regions or in this dense region. Then there are things like eccentricity. If the black holes are eccentric, then same things will happen. Because if they are going around for a very long time, then general relativity predicts that the orbits are going to circularize and they will become more and more circular orbit because the eccentric orbits emit much more gravitational wave. But then if they are in three-body interactions, like in this dense environment, they will remain eccentric because it is not that two things are going around for a long time. It is all kinds of things are happening. So all those things are there. So that is why people are trying to come up with algorithms which can take us to those more interesting searches. I mean, detecting these normal binaries are also fine, and then you can know how many such things are there, black holes are there, how they form, etc. But then, of course, you want to get to the more interesting ones so that you can go deeper in their understanding of their formation itself. So fine. So now the thing is that with all these detectors, data analysis algorithm, and by the way, many of these data analysis algorithms are developed at IUCAA. Okay, the fundamental. So all those things after that, where we come to that, why it was not detected for such a long time. So initially there was initial LIGO. So initial LIGO was built for operated I think till 2005. Okay, for 10 years I think it operated at 1/10 of the sensitivity. So why it was built? It was basically people knew that advanced LIGO will cost much more money, but initial LIGO was a technology demonstration. It's all about money. This is the thing. So then the government was convinced, that is US government, that such precision measurements are actually possible. So, but there the rates were like this, that the chances of detecting a neutron-star merger with initial LIGO was 0.02 per year. In other words, the chances that you would not detect was 98%. Okay. Now with advanced LIGO, what happens is that it has 10 times more sensitivity. That means it can see distances which are 10 times more. That means it can see volume which is 1,000 times more. So even though this looks 10 times, but it increases very significantly, and you see that it increased more than 10 times. The rates like 0.02 become 40 and so on. It is more than 10 times because the bandwidth of the advanced LIGO is also more than initial LIGO. So it can see integrate for a longer time. So this is how it is. So this is the initial LIGO's horizon distance. With advanced LIGO, this distance becomes 10 times, and now you can visually see that how big that is. But why it is so relevant? Because with this you are highly limited. In the next lecture, that is I think on Friday, I will tell you what is the next step, and there you will understand where we are and where we want to go. So finally, with all this, gravitational waves was detected, and this is this very interesting simulation which was done by the same set of kind of like the same codes which were used in the movie Interstellar. Rather, I should say that this was the code which was used for simulations by Kip Thorne and his group. By the way, this is quite interesting. The animation is running on my computer here, but not running here. Very, very unimpressive. Wait. Before, I think what I have to do is that you cannot compromise quality like this. Now let's see. No, not much, not that better. So, did anyone unmute? Because now hello. Okay, I think that got something. So the point is that all these interesting simulations are very difficult to do. Okay, it's not that it took a full team to make this because these are realistic simulations. What you see in that simulation is that there is a black hole, and behind that there is a galaxy, and the galaxy is getting lensed. And this was done like with all kinds of rigor in that for this event. And then this was done by this SXS team, and then so this Kip Thorne was involved there, and then later on this was this kind of things. If you even remember that Interstellar, those things which were used there. So see, there is so people talk about spin-offs of this. So this is the real spin-off. So cool. Meaning, entertainment is something which, of course, is essential for human life, right?
So this talking about the data analysis part, you said we need some sort of a signal that is already modeled or already known. How do we know that?
How do we know that? So that I think I said yesterday in yesterday's class, you see that the first part of the signal, which is the inspiral part, that can be kind of done analytically with post-Newtonian series and so on. Okay, in the first part, it is almost Newtonian. That is, you don't have to consider much. You just assume that this body is going around, and then you come up with some formula for how the orbit is going to shrink just by considering the energy loss. But then later on, it has to be more and more accurate. So this was done analytically, and this was done in India. In fact, a significant amount of work by Bala and so on. The next part, the last part, was the ring down part, which was also possible to do analytically, and there are professors, so Vishweshwara and so on, who did a lot of work on that. Okay. The same in between part, when they are merging, that requires numerical unit, and that can only be solved on big supercomputers. And I think I told you that it was very difficult to actually solve those initially, but later on people came up with some interesting coordinate system, etc., so that they could manage to do it. And that is again an open problem, because only in very specific situations we are able to get those signals right now. Getting a full numerical relativity simulation, for example, for all those 250,000 choices of parameters, is absolutely impossible right now. It is just out of the question. What people do is that they do some kind of hybrid models. For few cases, few choices of parameters, they get the signals, then they see that how to kind of stitch the signals. That is, now once you know for certain parameters how the signal will look like, they would try to predict from other sort of semi-analytical models that how the signal should look in the for in general case. So this is basically they do some kind of approximation like effective one body approximation and this kind of thing. So there, with numerical relativity for certain signal choices, they calibrate their model and then later on they use it for the whole template back. So this is how it is done. Okay. But this is again an open problem for many other choices. Like for example, when you put eccentricity, etc., these things are people are working on it. That how to include eccentricity as a model there. Eccentricity meaning the orbit is not exactly circular; it is somewhat asymmetric. I mean, it is you know what I mean, elliptical. Okay, so now the next thing, the first detection was that with two black holes. The next important thing which happened with gravitational wave detection was in 2017, August 17. That is how these sources are named. 17/08/17. Then you see the other one was 15/09/14. That is 2015, September 14. That's all. Now, the next was the binary neutron star merger. This was astronomically very, very significant. This is because black holes, when the black holes merge, they don't emit anything other than gravitational waves. But neutron stars emit many things in every electromagnetic waves, every wave pattern. This was first detected in so first detected by actually LIGO detectors, and then almost at the same time it was detected by gamma ray. Now, although this looks like 2 seconds later, LIGO's processing took somewhat longer and so on. But anyway, so almost at the same time this was detected, and then in various electromagnetic wave bands, this source was followed up. Okay, because this gave us a large amount of information about astronomy, fundamental physics, etc. So let's see one by one. So we will spend some time on this source because this is particularly interesting for gravitational wave astronomy. It's called the multi-messenger astronomy. This is the onset of multi-messenger astronomy. I told you, right, that thing that you take images in optical, X-ray, etc. for human body. It is very much similar to that. You get in different wavelengths and you get different information. The information did not come at the same time; they come somewhat later. Like radio, it comes weeks later. So first of all, the source localization. This is important to understand because this is what makes LIGO India very important. So what happens is that this was detected by Fermi. As I said, the signal came before Fermi to this thing. So that these two already told you that the source is somewhat here. But then there will be the LIGO ones. The two LIGO detectors detected this and that gave us some sort of error circle. Vargo did not detect, but that was important. That non-detection, even because it was sensitive, was important to rule out some regions on the sky. So then from there, they could basically point out that maybe it happened in somewhere there. And then people zoomed into that region, all these electromagnetic telescopes, and then they found that there is some activity which was happening in one of the galaxies. That's how they were able to detect the host galaxy for that event. Now, what is so important about detecting the host galaxy? Because as soon as you detect the host galaxy, you can get many different, look at spectral lines and find out the redshift of that galaxy. Okay? Now, already, what gravitational waves tell you, gravitational waves detection give you, are the masses of the binary components. Okay? So you know the masses because the masses are necessary to match the phasing. Now, since you know the masses, you can also say what should be its amplitude. Because masses also not only give you the phasor but also the amplitude. And you know what amplitude you have detected in your detector. By comparing that, you can get the distance to the source. Since you already have the host galaxy identified, you get the redshift. So this gives you the redshift versus distance, which will give you the Hubble constant. I don't know whether cosmology lectures have happened yet. Have happened? So then you will get the Hubble constant from this mechanism. So this is another way of measuring Hubble constant, and we'll come to that also. Now, first of all, the multi-messenger astronomy part. You see that this source has to be followed up for days to weeks continuously. So to see if there is any activity going on there. And obviously you cannot observe with electromagnetic astronomy except for radio in the daytime. So all the telescopes in the world have to participate in that. These Indian telescopes also participated. AstroSat did not see, but again, this non-observation of AstroSat was important for source localization because you can rule out that the source is not in this direction. So these things act as something called priors in your analysis, that you are ruling out regions or with that. Like Galgo did not detect that help. The GMRT did a lot of follow-up observation of that source for weeks. And Himalayan Chandra telescope also participated for that. Now let's see, we can see this animation properly. So with all these observations, then everything was put together in a very nice way. Well, this was too cool, but the whole thing was that there are many parts to it. Okay. These things were kind of people imagine that maybe something like this happened. But with all these observations together, people understood that this is what is happening. So there are, if you now look at the video again, you will see what happens is that first these guys are going around and there is a merger. After the merger, a jet comes out. Okay. And then that is called there is a prompt emission. Then the jet extends and it hits the interstellar medium. Okay? And then there is a afterglow that comes. All those things, the angles, etc., taking together, gave us a picture of what exactly happened during that process. So basically, they said that there is a cocoon-like structure that formed. It is not the jet coming out and things like that. There are many models which are considered, and finally, this model was passed through all the tests, and it took a very long time for people to figure out that what is the exact model. And many papers were written at that time. So you see now that even though this movie looked very beautiful, it also actually shows all these components. And it is important that even one detection of this gave us so much information. So now you will see. See, this is the spiral. There will be a tidal sort of disruption near the end. See, the jet came out. Now this is the first emission, and then there is this afterglow. Okay, and that is the bend. Okay, so now here is the thing. So this is also something interesting to see. When we are talking about other gravitational sources, there are very different time scales. See, this is depending on the mass. More massive there, the signal becomes much shorter. So this one is very short. This one is somewhat longer. And the neutron star ones are very long. And that is because they merge at a much higher frequency. What happens is that if the source is, the inner planets have a lot smaller period. So if the source, if they could reach, if they could come close, then the period will be larger. But for big fat black holes, they touch much earlier. So then they cannot go to that high frequency, they march at a lower frequency. But for these thin neutron stars, they can come much closer. So which is why they go to much higher frequency. And then they stay also very long time in the detector stack. So which is why, which allows us to detect neutron stars uh, from a reasonable distance. Because otherwise what happens is that the black holes are far more energetic, but then because they are this wave, meaning the signal is shorter, that somewhat compensates for the long signal of neutron stars. But these neutron star black hole signals, you could still kind of see in the data. It is not completely embedded in the noise. But neutron star signal is completely embedded in the noise. You have to use this match filtering technique to, or some other this thing to, techniques to make the signal, integrate the signal for a long time. So now there is a fundamental physics question. I think some people asked yesterday, okay, the gravitational wave travel at the speed of light. From Einstein's theory of relativity, they do. Okay, but then you always need to prove that. So this was the proof that came. Oh, I have to. This is the sound of gravitational wave. I will play it again. So you see that because gravitational waves are in this audio frequency, they just take the signal and put it to a speaker, and it will create sound which we will be able to hear. So that is the church signal. You will see that amplitude and phase are amplitude and frequency are increasing with time. Now, once the signal is received, there is the gamma ray signal thing which is also given at the same time. Oh, sorry. This is too complicated. So this one comes 2 seconds after the gravitational wave. Okay. Now, what does it tell us? Light to come to us. The gravitational wave signal came 2 seconds before that, so which means that the velocity of gravitational waves and electromagnetic waves are close to of the order of 1 part in 10 to the 16, right? Because that it is like only the fractional difference is that small. So which almost gives you a confidence that probably they are the same. But still people work on seeing that if there are deviations from general theory of relativity, which can explain such things. The 2 second could be an observational artifact, could be that the signal, the electromagnetic signal, the gamma ray signal was actually emitted 2 seconds afterwards, or it could be that it was emitted at the same time, but then the medium was so dense that the velocity of light was slightly lower at that in that part, and all kinds of things are possible. So people who were looking into it, I did not follow that what happens afterwards, because most likely they are the same. I don't have to worry about it. So now there are many other things which came out of this. One of the most interesting things was the generation of the heavy elements. You see that, that we started with, let's say, electrons and protons which combine to form neutral hydrogen. Then from there you start forming stars, you do fission, fusion, and then it creates heavier and heavier elements. But you also know this nuclear binding energy curve, right? So at some point you will hit a maximum. Now the question is that how do you then create heavier elements? Because no process, see all these processes are exothermic processes, right? Which will basically, once something happens, it has to emit energy. Because otherwise, that is the final system has to have lower energy. But you cannot have a process you cannot, then how will you create these heavy elements which are at a higher energy? Because no natural processes generally don't get into higher energy. So one of the possibilities was that supernova. During supernova, this very high energy collisions happen. Maybe heavy elements, meaning somewhat not heavy but less heavy elements, will collide to form heavier elements. But that could not explain the whole percentage of material that we see, especially gold. I think many of you must be wearing gold, silver, etc. How did they come from on the Earth? The primary channel, which turns out to be a merging neutron stars. The black holes, of course, cannot, even if there are whatever gold, platinum, whatever, they will stay inside. Okay, useless. But for neutron stars, these things will merge and they will create those heavy elements. Okay, without the heavy elements, we could not even have this presentation because there is a lot of heavy element involved in this. We would need some very different technology. So the thing is that, so this was another thing that we learned, basically with these follow-up observations, etc., that heavy elements are indeed forming in those binary neutron stars. This will become more and more concrete after we have many more detections. So far we have only one, unfortunately, and we are somewhat statistically favored, but in other words lucky, that the event happened actually very close, like 40 megaparsec away. The probability of such event at such a close distance is very low. Okay, now moving on. So this is another very interesting thing that happened. So this part I have already said, like what we learned. But now we come to the Hubble constant part. So I told you that you can get the luminosity distance as well as the redshift of the host galaxy from this kind of binary neutron star merger observations, especially for this GW17870. So if you take the ratio, you get Hubble constant. The Hubble constant tells you that what would be the velocity. So V is equal to H naught D. So if you know V and D, then you can get H naught basically. That is the current epoch for this purpose. Now you see that there are two measurements of Hubble constants, two very precise measurements of Hubble constant which are right now available. One from the cosmic microwave background observations, another one from supernova observations. Okay. These things are very precise, okay, but they don't match. It is like scientists, they are very confident about their results, but they just don't match. So this is now the thing is that how do you then resolve this problem? Okay? Because clearly one of them is wrong. Both cannot be correct because there is no overlap, right? They are significantly far away. I think there are 5 sigma this thing. That is the probability that this is a statistical fluctuation. That is, they are actually the same, but just because of different kind of noise or whatever, we are getting this separation. Is some 1 part in 10 to the 4 or something like that. Is almost negligible. So most likely, this is one of them is wrong. So if you get an independent measurement channel, independent way of measuring the Hubble constant, then you would be able to say which one is correct. With the present measurement, the error is here, is big. But the thing is that more and more, when more and more detections happen, this error is going to shrink. And at some point, we will be able to say which one of these is incorrect, or if both are wrong. Okay. But hopefully that will not be the case. At least one is correct, so that then we can confidently say that the other experiment is wrong. Okay. So here is the thing. So after the first years of gravitational wave astronomy, here we stand. Okay, we have about 100 detections of various sizes and so on. But as you can see, this is still the beginning. Okay, because we have only detected this same kind of sources in a given frequency band. There is a whole lot of way to go. You can perhaps compare this with Galileo's detection of planets. We are basically there, like one kind of source we have detected. Like Galileo detected these planets in optical band, and we have detected these mergers in frequency band. So then the thing is that what are the next steps? Okay. First, we have to, so the last lecture will be more on this slide, but today it's like kind of a summary. So you have to build a network of detectors. Why do we need to build a network of detectors? Because we want much more precise source localization and want to detect many more sources. This I will tell you about. That is the main reason for LIGO India. Then the other thing is that we have to improve the sensitivities of the instruments and enter the next generation. It's like you know, first there was initial LIGO, which could not detect anything. Then we improved the sensitivities by a factor of 10. Then it started detecting many things. Now we have to go to another major change. So from initial LIGO to advanced LIGO, there are major changes, like the mirror size, mirror weight, mass, changed from 10 kg to 40 kg. Then, the laser power increased from 2 watts to 70 watts. So these kind of massive changes are going to happen, and then we will enter next generation detector. But one of the problem of next generation, one of the ambitious plan for the next generation detector is to also increase the arm length quite significantly to 10 kilometer to 40 kilometers. Okay, so these are the kind of plans which are going. Now, and also, as I am saying, keeping repeating that we are observing at the single frequency right now, in the single frequency band. We have to go to many other frequencies. But you cannot go to other frequency band on the ground. Because, especially the lower frequency, high frequency, we don't know there are sources. Lower frequency is completely, it's almost impossible to beat the seismic noise, which is there on the earth. Also the anthropogenic noise that we create, like that. The noise that comes from the ocean is called the microseismic noise. Okay, so which is why you cannot, it is not preferred to build a detector close to an ocean. All those things are there, even though the Italian detector is fairly close. So, basically, we need to either go to space or we can also do something called the pulsar timing array to detect gravitational waves. I'm not sure whether I think maybe somebody will talk about pulsar timing here. Rashwan Gupta is giving a talk on space case. So he'll most likely talk about pulsar timing array. Now, right now, for us, the most important thing is LIGO India. Because if we can do LIGO India, then we can use that knowledge and expertise to build maybe space-based detectors. So all those things will happen in the next lecture. Okay? So not happen meaning all those discussions will happen in the detection. Now there are what are you going to do with all this? There are fundamental questions. Very few, but there are many more. First of all, is Einstein's general relativity is the correct theory of gravitation? This is a very important question. You could say that, yeah, it must be correct. Like, but then, as I said, like, similarly, maybe Einstein's theory is correct to a certain extent, but it probably breaks down at a certain limit. Like, for example, at a very high energy limit, maybe Einstein's theory is no longer valid. Is because most likely there is no singularity also. Okay, singularities are very difficult to believe. Maybe there is quantum gravity. If there is quantum gravity, then that effect will come into the picture. So all kinds of things are connected. Then there is the other side of it. The people are trying to explain dark matter and dark energy with modifications to general relativity. If that happens, maybe there will be implications on gravitational. So finally, we need to see whether Einstein's theory is the correct theory and gravitational waves can probe the high energy limit, like where the curvature is really high.
Yes. Finding the gravitational waves, the template that we built it on the assumption that
that is absolutely correct. Yes.
And how can we find something that is resolving?
That is the thing that so this is the problem that we cannot, unless we create templates for the with some other theory, we will not be able to say whether the other theory is correct. But we can still find deviations. Okay. In this way, that suppose so there are different tests people do. One of the primary tests of which are proposed is so one of the primary predictions of Einstein's theory is something called the no-hair theorem for black holes. That is, the final black hole that is formed a black hole, forget about fiber black hole, a black hole is characterized only by its mass, charge, and angular momentum. Okay? Now, it is also shown that if there are some perturbations to the black hole, the perturbed modes will depend only on these three parameters. Now you go back to the first part and say that during the inspiral part, you have a very precise idea about the masses of the individual black holes. Since you know the masses of the individual black holes, you know what should be the final mass from general theory of relativity, from Einstein's theory. Now you go to the second part, and from this other part of it, from the ring down part of it, using Einstein's theory, to calculate the masses. Okay? Because they depend only on the masses, charge is basically, people assume they are neutral. So mass and angular momentum. The angular momentum also you can guess from the first part, because this orbital angular momentum is conserved. So it will become basically the spin angular momentum of the final black. So from the first part you have predicted what should happen in the second part. Now, if you do this analysis, then you can do something called the IMR consistency check. That is inspiral merger ring down consistency. That will tell you whether, if Einstein's theory is really correct, then these two parts should be consistent. Okay, this is one part. Second part is, so this is one way of one test of Einstein's theory. And the second part is that when we are doing these templates need not be absolutely correct in order to have a detection. So suppose you have detected a signal. Okay. Now you can say that, let's say there are these post-Newtonian terms. Okay, there are this approximation which was used to find the template. Now let's try to find out how much the signal is actually deviating from those. Okay, and then you come up with some deviation parameters. Okay. Now you assume this, and this is probably the very reasonable assumption, that if there is a different theory of general relativity, it is quite likely that that theory is also universal. Meaning, it is not that there will be one theory of relativity for one source and another theory for another source, nothing like that. So now what you can do, you get these deviations and try to constrain them with all the observations you have done. Then you see whether this theory is exactly following the post-Newtonian terms which you have predicted, or there are deviations. But I think for those things, you need to get the parameters of every other parameters very precisely, like speeds, etc., which we are ignoring. I don't know how you can do this test. I don't work on this, and I don't know if you can actually do such tests at this point meaningfully. You need much better detectors in order to, when you have very precise model for the signal. I mean, what is observed has to be known clearly. If there is too much noise, you cannot find those deviations reliably. So these are the things which people do. So these are called the test of general relativity. There are papers there. You can look at it and see what kind of tests people are doing. Okay. Now the other question, like for example, is there an event horizon? Okay. The thing is that this is also very interesting, that there is no direct proof yet, other than the event horizon telescope, that there is actually an event horizon the way we think about it. Okay, I have to see whether I have a video. I will show you that in the end. So these are because if there is an event horizon, then that is another proof of generality. That we know that okay, it is there. Okay? And there is a very interesting proof that can come from gravitational observation. Then I said many other things, that how exactly the universe is expanding. So one thing is to get the Hubble constant at the present epoch, which is called H0. But also, if you want to see how dark energy evolved with time, you need to get the Hubble parameter at different redshifts. That can also happen with gravitational observation, but probably not with the present detectors only. You need space-based AC Hertz detectors and so on. We'll come there in the next one. And then there was, like, for example, cosmological inflation, etc. Meaning you can see that these are fundamental questions, what I have written. But there is a whole bunch of questions which were listed in something called the a Gravitational Wave International Council roadmap. You can just do a Google search, you can find it there. It's a huge set of things which we can do with gravitational wave astronomy. Okay? Okay, so I will stop here and I will try to find out that interesting video, if I have it here, to show how you can probe event horizon.
Online participant can raise your hand.
This last part, you see what happened is that in the last part, this suddenly stopped. Because as soon as the small black hole enters the bigger black hole, the wave, the whole thing suddenly stops. This sudden stop signifies an event horizon. Now, actually, in practice, it can never get into the black hole, the bigger black hole, because time slows down significantly and so on. So it will basically get infinitely redshifted, but it will happen very, very almost instantaneously. And that will be a very solid proof that there is a sharp cutoff in the signal. Okay. Yeah. So this is one of the things. Okay. That's it. Now I will come back to the question that somebody. Actually, by the way, you have any questions? You can also think about it. You have a question?
The waves would get redshifted.
Yeah.
So does that change the?
It is not exactly the waves are getting redshifted because it is the whole system which is emitting the waves. So it is not when people are solving for these equations, those redshifts etc. are all incorporated. But what is meant by infinite redshift is that this object will suddenly slow down completely and you would not see any change in the quadrupole moment. Okay, which would create, there will be a very small change at a very low frequency. So that way the whole wave will get redshifted to a lower frequency.
I wasn't asking about this, I was asking in general.
Oh, in general, yeah, these are all redshifted.
So
the wave, suppose a binary black hole merger happens at redshift of 1, the frequency will be redshifted by a factor of 2, that is 1 plus z.
Then how do you find out?
which template to match?
So the thing is that there is a degeneracy that the mass, what you actually measure is like 1 plus z times mass. Okay, but that you can fold in when you are solving for the equation. So meaning ultimately you want to measure. So you have two equations. V equal to H naught into D. Okay, the other equation. So this what you have already got is the redshift from the galaxy observations, right? So that is giving you V. Okay, and then the other one you have got mass. There also there is a redshift term. So you could actually solve for it. The masses from the so basically the mass says with this redshift factor will give you the phase, and then also when you are getting D, the luminosity distance, you can put this 1 plus z factor here, and then finally solve and get it. So you have two independent observations anyway.
I just want to ask that what makes the stars explode? Like it is because of the supernovae or burst of gravitational waves?
So stars explode because of supernovae. There is no other thing. But here it is not exactly exploding like that, but there could be an explosion also. Like for example, what you saw in the binary neutron star, they suddenly collided. It's a proper collision of two, like this, essentially soup of neutrons. They collided at very high energy, okay? And that created all the kind of radiation, particle, etc. But it also created a black hole. Probably it can create a black hole in the end, even though we don't know if this particular one what you saw, what there was a black hole or not. Okay? By the way, this redshift question you asked, you could think about this way. But suppose you had an electromagnetic follower, you got the redshift already. So then you know the mass you have detected is the apparent mass divided by 1 plus z. So then you can back calculate.
But if it's a black hole, then you can't.
For black hole, it's more complicated. Because for a black hole, you cannot get the host galaxy so easily, at least at this point. But you have a group of galaxies which you can identify. Suppose you know from where black hole merger has happened. So you have the location and you also have some kind of idea about the distance. You know how many galaxies are there. Now assume for each galaxy, you find out the Hubble constant, and then do an averaging. So you basically don't know each one of the exact one, and then you can follow the same procedure because you don't know it, but then you can kind of try to get some idea. All you need is the velocity and distance.
Also, do they lose angular momentum or just energy? Like when the merging is happening, is the angular momentum conserved?
Angular momentum is essentially conserved, yeah. No, angular momentum is conserved. Gravitational waves will carry a little bit of it, but then that is, I think, folded in. Effectively, basically, the total angular momentum, final angular momentum, that is the spin of the final black hole, is almost like the orbital angular momentum of the system. The individual ones should not matter so much. Or maybe they will. Yeah, I mean, the total angular momentum maybe will matter. Yes?
The image of black holes that would develop that should confirm event horizon.
At that, we'll have to debate on this, like whether the event horizon certainly tells you that there is a dark patch, there is a black hole there. Whether there is it's a bit fuzzy. I may be biased towards gravitational waves. I cannot really call it an event horizon. An event horizon is a sharp surface. It's like where things get infinitely redshifted and so on. It does look like there is a black hole, but I don't know whether it can be called an event horizon as yet. You see what I mean saying, right? You see the lensed image, what you see in the event horizon telescope, the dark patch, and there is the lensed light which is coming to you. It is like those interstellar light picture. Okay. Now, does it tell you that there is a precise event horizon or not? I am not very sure. But if something like this happens, then you know that that cutoff is so sharp that probably there is an event, a more direct. But I think radio astronomers will doubt, will say that no, this is like a time series signal, and there you see the direct thing. There will be some debates.
So yesterday I was reading about the gravitational waves. So there was a term called cosmic strings. So I didn't able to understand it. Like there was written that burst of gravitational waves detected the cosmic string. So what does it mean?
Nothing. Cosmic strings have not been detected. It's a speculative theory. It is, but then many people work on it. Cosmic strings are they're called some kind of topological defects found in the early universe. If you could imagine those higher dimensional surfaces and there are suppose some kind of strings, etc. in those, okay, then those strings can oscillate and they will generate gravitational waves. The strings also has this property of they create loops. Okay, as they create loops, they get separated out, and then they emit gravitational waves. This loop is emitting gravitational waves. As they emit gravitational waves, they shrink, and then they finally vanish, and things like that. Yeah, but I don't want to comment on those things. Those are very speculative. Yes.
Match filtering.
Yeah.
So this match filtering accounts for the non-linear time variance because the mean filter, the filter you talk about, it's traditionally like a linear time variance. So what we are replacing that match filtering. Is match filtering accounting for the non-linear changes of
non-linear changes of what?
Basically, there's a gravitational wave. It's coming from.
Oh yeah. That's like when the filter is designed, the filter meaning the waveform. When people are solving for the waveform, then those non-linearities are already taken into account. The thing is that analytically you can only get on up to certain part. Okay, with all this post-neutrino, etc. After that, you have to use numerical relativity or quantities derived from numerical relativity to get the full nonlinear solution.
There's a filter and there's a gain involved. So, are we adjusting the gain based on our predictions, or is it?
It is independent of the gain. Is like the amplitude of the filter. It is independent of that. The way we normalize the signal is that after mass filtering, the variance of the observed quantity, what pure noise should be 1. So then, because if you can always multiply with any amplitude, it does not change anything.
Correlation is taken as observed data in front of observed data and connected.
Yes, and normalization, which would be your gain, is done in such a way that the variance is 1, so that it becomes easy. So when you do the correlation, what you get is the signal to noise ratio. I did not say what the signal to noise ratio is. Signal to noise ratio is of any quantity that you measure. Suppose you are trying to measure a quantity x. Okay. Suppose you are trying to measure a quantity x. Okay, and this has an expectation value which is equal to mu. Okay, but when you do the measurement, x will be equal to some mu plus some noise, because you will obviously not get exactly the same value, right? Then, if you take the variance of this noise, so let's say the sigma square is equal to variance of let's say x. And this variance is essentially coming from this noise. Okay. Then your signal to noise ratio. So yes, this signal to noise ratio would be this mean divided by sigma. This is the variance of essentially the noise, and this is the signal you are detecting. Okay, so basically this means that if you see this kind of this thing we saw, there was something and So how will you say, when can you say that this peak is significant? Is this significant? Is this significant? This is the problem. So then you take the variance, and let's say that variance is up to this level. Then you say, let's say this is 0. This is 0, and this is the variance. Then you can say that well, for a 5 sigma detection, that is the probability that a statistical fluctuation, noise, can give rise to this. It's 1 part in, let's say, to the 4 or something. Then you make 5. If something is above this, then you call it. So this is basically for each one. So now, if you normalize in such a way that the sigma is basically 1 for noise, then your whatever you are trying to measure with this match filter, it will be a direct estimator for the signal to noise ratio. That's what it is. Okay? It will not be exactly x, it will be some y, which is a linear combination of x. And that's in such a way that the linear combination of this noise with that quantity has a variance of 1. I mean, this is trivial actually, you can do it. I mean, it's not necessary, but you can do it that way. Yes.
So how this initial matching happens? That is what signal is coming and how we are applying some template.
So you or for every bit of data that is coming, time series data, all these 2,000 and 250,000 templates are applied to that. So continuously it happens. Okay, it is called an online search. But this search does a bit in a way that it does not get into too much details. It's not a deep search. It's a very quick. It's called low latency search, so that you can find the potential triggers. Okay, and also there are other things which happens, like in parallel, people try to find out what are the glitches. So there are always glitches in the detector. Okay, that means a truck passing by, something. Many times we don't even know what is causing this. Some kind of glitch. Glitch means some extra signal and this thing. So finding those out also happens in parallel. That okay, people keep marking. People meaning now there are automated softwares which basically with machine learning based sometimes they mark that there are glitches. Now when there is a trigger like this, people see that whether the trigger really came because of the glitch. Because even though match filter, a match will happen when the signal is exactly matching. But suppose the signal is extremely large, okay, the noise is extremely large, then just by statistical take some number, multiply with a very large number, even though the expectation could be 0, it's just statistically sometimes signal will become very large. So those are also flat. Okay. So after that, when people, then there are different teams which can do this work. That okay, as soon as there is a trigger, people get into that data manually and see what was there at that time. Was the detector working properly, etc. Once that happens, then people claim there is an alert which is sent to the community, whoever is interested, that we have found something potentially interesting. You may want to look at it with your telescope. This kind of things happen. But the final analysis, where actually the analysis is done properly, which will give you much more accuracy, and the parameter estimation for the sources, that is done much later. It usually takes some time.
Is there any way to classify the data set and kind of reduce the number of data that you have?
I don't know. No, I don't think so. One way would be to probably look for the triggers, which is where the energy is slightly higher, meaning there is some possibility of a signal. But see that if you do that, the neutron star matter signals will just be missed because they are very, very faint but very long. The black hole signals you may detect as some extra fluctuation in the data, but the neutron star signal is so faint that you will just miss it.
Sanjit, there is a question online.
Right. There was a question that
What are the other effects of gravitational waves other than displacement of test
So
masses?
the thing is that gravitational waves are metric fluctuations. So in order to get the effect, you need the test masses to see how the distance is fluctuating in between, because that is how you probe the metric. So there are, I don't see there are any other effects other than that. The primordial gravitational waves did have a signature on cosmic microwave background polarization. So if we can measure that, then that will be an indirect effect. And then, like that Hubble stellar binary pulsar, which basically that orbit was shrinking, that was because it was emitting gravitational waves. That is another effect. So other than that, there is no other effect. I mean, in fact, for bar detectors, you can say, even though it could be considered as a test mass, but then bar detectors do get a ringing, that is a resonant oscillations happen. So that's another way of saying it. Okay. Okay, I think we will now stop and we will meet again on Friday at 4.